confirmation about the audio, please, guys. If the audio is clear and available, kindly confirm the same. Thank you. We shall be starting in a couple of moments. Vikram, the reason that you can ascribe to the shifting of the axial tilt is basically that planet is a kind of a spherical object. It is not a perfect sphere. It is slightly bulged around the region of equator. So imagine a sphere which is consistently rotating out there in space or in lack of air whatsoever. So the center of gravity in itself and the center of mass that keeps on changing with respect to time over a period of time as the planet rotates. For example, you would also have seen that, for example, if you would have in your childhood days, you would have seen a spinning top. Now that spinning top, if you rotate it, or any ball that you rotate, it is not always going to be rotating at the same place in the same way. It keeps on having some amount of tilt here and there. So that is how the planet's mass in itself is responsible for that shift. So after some time, the axial tilt basically after every around 26,000 years, the axial tilt increases to around 24 degrees. 24 degrees, and then when it tilts significantly, then the other bulge or the other side of it over a period of time pulls it back, takes it to somewhere around 21 degrees. So that kind of 21 to 24 degrees of shift is always there. Okay. So hello, a very warm good evening to all of you and welcome to BYJU'S Exam Prep IAS. Welcome to another session of geography where here we shall be continuing our discussion where we left off yesterday. So yesterday we looked at some of the basic concepts about the origin of universe. We looked at the theory of expanding universe provided by Edwin Hubble. Then we looked into the portion of Big Bang theory which was provided by Lemaitre and Gamow and what the concept of it was. Then we looked at planet Earth as a rotating and a revolving object, as planet Earth basically would move around the sun. Now it takes around 365 days to complete one movement. And it is because of the axial tilt of the planet that different areas they get varying amount of exposure to solar rays. So as a result of that, you have certain months of the year where you will find that there is a greater duration of daytime in certain areas and greater duration of nighttime in certain parts of the year. So that variation in the length of the day and night is also created due to that axial tilt, which leads to the occurrence of various different seasons. We looked at the concept of latitudes and longitudes, how to number them. And now, today we shall be initiating the discussion from international dateline. Moving ahead, we will be moving into the portion of geomorphology finally, where we shall be talking about the origin of planet Earth. How is it that planet Earth came into existence? We shall also be taking a look into the aspect of the interior structure of planet Earth. What is the interior composed of? What are our sources of information when it comes to the interior of planet Earth? And basic types of the rocks, basic information about the rock types that we have, that we find around us. And then we shall be proceeding ahead with some of the important theories of geomorphology, that is the continental drift theory, the convection current theory, the seafloor spreading theory, and how all these theories eventually helped us understand the theory of plate tectonics. So here, first of all, we initiate the discussion from international dateline. Now, what is the international date line? So again, it is a kind of an imaginary line which is demarcated, which ends up differentiating one day from the other, right? So, in order to understand that, for example, let's suppose we consider this to be the prime meridian, which passes through Greenwich near London. That is your prime meridian. Okay. Now, as I told you yesterday itself, that this prime meridian is used as a reference pointer in order to keep track of the time, and the time observed at that prime meridian is also referred to as the international standard time, or basically universal time, or the Greenwich Mean Time. So it is the reference time followed internationally. Now here, various different longitudinal extents rather, they help us understand what is the time experienced in different areas. For example, when we talk about Indian Standard Time. Now, Indian Standard Time is 5.5 hours ahead of the time observed in Greenwich. Why that is the case is because India lies to the east of Greenwich, or India lies to the east of London here, right? India is here, Greenwich is here. So obviously the sunrise will happen much earlier in the case of India, right? We will experience sunrise and sunset much earlier as compared to London, right? So Indian Standard Time overall, when you consider Indian Standard Time, Indian Standard Time is 5.5 hours ahead of GMT. Or Greenwich Mean Time. Right, 5.5 hours ahead of GMT. Now here, when we say, let's suppose, what this actually means is, it is also represented as GMT plus 5.5 hours. So, if in India it is, let's suppose, 5 p.m. as of now. Let's suppose it is 5 p.m. in India. So what will be the time observed in Greenwich near London? What do you think? What will be the time observed in Greenwich in London? So for that, you have to subtract 5.5 hours, right? So it will be roughly around 11:30 a.m. Very good. So if in India it is 5 p.m., then in the region of Greenwich, it will be 11:30 a.m. Okay, so that is the case of the time zones which we generally observe. Now, if I take you to this particular image here, let's suppose here, if you notice, in this image, it is written +1, +2, +3, +4, +5. That means these are the regions which will experience sunrise first and earlier as compared to the region of London or Greenwich, because the planet continues to rotate in a direction of west to east. So obviously, as it rotates from west to east, this portion which is on the east will experience sunrise first, will experience sunset also. So as you can see, +10, +11, and so on. So if you are present in the eastern portion of Siberia, let's suppose. So this is indicating +12. That means GMT +12. So if it is, as we have seen, if in Greenwich right now, in Greenwich it is 11:30 a.m. So what will be the time in the region here in Siberia? If in Greenwich, if GMT right now, let's suppose, is 11:30 a.m. So what will be the time here? Very good. It is plus 12. So in this region, it will be 11:30 p.m. At night, 11:30 p.m. at night. That is the time which will be observed there. But if we go here on the other side, you observe -1, -2, -3, -4. So that means the sunrise is happening here after what you observe in the region of London. Right? Sunrise is happening after that. So around 180 degrees longitude, that is in the region of anti-meridian, you come across a scenario close to around 180-degree latitude, that is around the region of anti-meridian. You will observe -12, -11, -10. So here in Alaska, you observe the time GMT -11. This is your GMT -11. So what will be the time here right now? If at GMT it is 11:30 base AM, so what will be the time observed in Alaska as of now? -11 hours you have to do. Very good. It will be 12:30 AM. Here, 12:30 AM. So in Alaska, it is night time, but it is basically 12:30 AM of 14th of December, isn't it? So here, sunrise of 14th of December is still to happen, isn't it? So that is where the entire region will experience. Basically, we have almost done living with the 14th of December. We are done with the date of 14th of December, and tomorrow it will be 15th of December. But the region of US, the region of Alaska, basically right now it is night time there, and they will be waking up in the morning in a few hours. So basically, there, because the planet rotates on west to east continuously, you will have night time here also, but that will be the night of 11:30 p.m. of 14th of December here. 14th December, isn't it? Here it is early morning of 14th of December. So in half an hour, around half an hour to 1 hour, Siberia will be entering into 15th of December, because it is 11:30 p.m. there. So in half an hour, they will be entering into the new date, that is around 15th of December. But what about the region of US? US, after a few hours, will be experiencing its sunrise, and then it will be experiencing 14th of December. Then after that, after 24 hours, then they will be entering into the era of 15th of December, or the date of 15th of December. Right. So that is the case where you have around 180-degree latitude, longitude, that is what is referred to as the anti-meridian. Around the region of anti-meridian, you have that imaginary line which is referred to as the international date line, which differentiates one day from the next. That is your international date line. It is almost in the region of anti-meridian, but this is not a straight line like other longitudes. It is quite a zigzag line, as you can see. And that zigzag lineation is basically because of the fact that you have the case that if, let's suppose, if this line would have been straight, let's suppose this line would have been straight, so it would have cut countries' borders into half. So the same country would have experienced two different dates simultaneously. So that obviously would not make sense. So in order to avoid the borders of the country, so that to ensure that a country at one particular time experiences only one particular date, that is where you will find that the IDL is quite zigzag here. Okay, so that is the case of IDL. Now, here, when we talk about the IDL, what happens if you cross the IDL from here to the other side or either side? That is something that we have to know about. So the date line is not straight, ideal is not straight basically. So the date line runs from North Pole to South Pole and marks the divide between the Western and the Eastern Hemisphere also. It is not straight but zigzags to avoid political and country borders. Okay. And it is so as to ensure that not to cut some countries in half. That is why the ideal is basically a zigzag line. Now, when we talk about the IDL, let's suppose we talk about the IDL here. Okay, a random rough image, let's suppose. Let's suppose this is your IDL. Now, this portion will be considered west of IDL. This portion will be considered east of IDL, international date line. So, if let's suppose we are talking about the region of US, now United States is to the east of IDL. If we talk about, let's suppose, Japan, Japan is basically to the west of IDL, isn't it? So you have to the east and to the west of IDL. Now, here, let's suppose someone crosses from Japan to US or someone comes from US to Japan. What will be the adjustment that they have to make? For example, let's suppose in half an hour, we have seen that the region of Siberia, the region of Japan, will basically be experiencing 15th of December. Let's suppose you have your birthday on 14th of December, and here you have 14th, let's suppose, and here you have 13th. Okay, because here the next day is still about to come. So as the planet rotates, basically, this will also experience the new day. But let's suppose as an individual, you are moving from the region, you have basically taken a flight. Let's suppose you have your birthday on 14th of December. You take a flight from the region of Japan and you fly into US, let's suppose. Now, in that case, what will happen? There, you will again come to encounter 14th of December. You will get to relive that day again. So, in a way, in your life, you are living that day again. Here also, you have celebrated your birthday, and after one day, you are moving into the other region. But maybe you have taken a flight, moved by a boat, or whatever. But then again, you get to experience that 14th of December. So, we can say that in your life, you have gained a day, isn't it? So, when you cross from west to east, when crossing from west to east, you gain a day. We can say that basically you end up gaining a day because you get to live 14th of December again. So gain a day in your life. Now, how will you adjust? Let's suppose in your watches you have your calendars or the date marker in your watches. Your watch is indicating 14th of December, and you have reached a region where it is still 13th of December, which is being celebrated. So, how will you adjust your watches there? What will you do? You basically will have to subtract a day in your clocks, in your calendars, everywhere. You have to subtract a day in order to adjust to that new area, isn't it? So in this case, we talk about subtract a day. But what if, let's suppose you are catching a flight from US and you are moving to Japan. In US, you were basically experiencing and celebrating 13th of December. By the time that you land in Japan, you find out that there it is 14th of December night. So basically, you have almost lost a day, because that day basically you have lost it, because there while you were in US, the sunrise still had not happened. It was still 13th of December, and then you suddenly crossed over to US, to Japan, where 14th of December is almost over. So when you cross from east to west, crossing from east to west, east to west, You tend to lose a day. Okay, you tend to lose a day in your life. But how will you adjust your watches in that case? While you were basically experiencing and celebrating 13th of December there, now while you have reached Japan, you are experiencing and celebrating 14th of December. So you will have to add a day in your calendars, clocks, watches, everywhere. You have to add a day. So that is the adjustment that you do when you cross the international date line. Why do we have to adjust? You don't adjust, but basically when you reach that area, if your watches and the clocks, they indicate the previous date and that region is celebrating or experiencing a new day, you will have to basically shift that clock, isn't it? So that is the case of the adjustments that you make when you cross the ideal from either east or to the west. Now, those of you who have a doubt that US is to the west, Japan is to the east, now all of that is with reference to where? With reference to India? Ankush, you have that doubt. Japan is on the eastern side and US is on the west. With reference to what do you say that Japan is to the east and US is to the west? Direction is never absolute. Direction is always relative. For example, is India to the east or is India to the west? If I ask you this question, what will you write? That is India to the east or to the west? Let me know. India is to the... Now again, I will have east also, west also. But when I say with reference or with respect to Japan, is India to the east or to the west? Can you say that India is to the east of Japan? No. India is to the west of Japan. But if you talk with respect to Pakistan, India is to the east of Pakistan, isn't it? So direction is never absolute. Direction is always relative. So when we are having the relative marker as international date line, so with that respect, US is considered to be the east and Japan is considered to be the west. If you consider, let's suppose, India, then you can say Japan is to the east and US is to the west. Okay, but that direction cannot be paramount and cannot be fixed for every place. I hope you are understanding that. Okay, so that is the case of ideal. So what happens when you cross the ideal? So when you cross the ideal from west to east, that is from the direction or from the region of west of ideal, this is your ideal, from the west to the east, you end up gaining a day in your life. And that is where basically when you gain a day, you have to subtract one day in your clocks and calendars. So that is where you subtract a day. And if you cross from east to west, vice versa, you tend to lose a day because the other region would have experienced sunrise at that point of time. The other region would have experienced the conditions of the next day also. So you have to add a day in your clocks and calendars. Okay, so that is basically the case of ideal and what happens when you crisscross the region of international date line. Now this is a particular portion which is relevant for your prelims. What happens when you cross the ideal? Okay, now then we come to the various systems of planet Earth. So when we talk about planet Earth, basically it is composed of various different, it is said to be composed of major systems which drive the features of the planet. For example, we have the lithosphere, hydrosphere, atmosphere, biosphere, and what is also known as cryosphere. What are these? So lithosphere, the surface or the ground on which we stand, that is what is known as lithosphere. Okay, so lithosphere is the surface or the ground that we stand upon. Okay, I'll tell you the exact technical detail of lithosphere also when we talk about the interior structure of planet Earth. But the surface on which we are standing upon, that is your lithosphere. Hydrosphere, all the water bodies, the seas and the oceans of the world, they end up dominating and forming what is known as hydrosphere. Then the blanket of air which surrounds the surface, which surrounds the planet, that is what is referred to as the atmosphere. Now, biosphere, all the living beings on the planet, all the living beings living on the planet, that is what is known as the biosphere. That is what composes the biosphere. And then what is cryosphere? What do we understand when we talk about cryosphere? Cryosphere represents the frozen regions of the planet. That is, the polar areas, they are frozen. The third pole, the Himalayan region, which consists of one of the largest masses of ice outside the North and the South Pole, that is also a frozen area. So, all these basically are included in the portion of cryosphere. It is the interplay between these systems which are responsible for the conditions that we see around us and the conditions in which we tend to live. Okay. Now, here we talk about, first of all, the basic terminologies that you will come across in the portion of geomorphology. And when we talk about the portion of geomorphology here, you come across lofty peaks, very lofty pointed peaks. These are your mountains. So this is the image of Mount Everest, the tallest mountain peak across the planet. So this is your mountain. So in the case of a mountain, you will find certain features. For example, you will find that in the case of a mountain, the peak is always pointed. It will have a conical and a pointed peak out there, right? It will generally have sharp edges around it, and it will end up having a kind of a distinct conical peak. It is going to be very high. The gradient, the slope is going to be very steep here. Okay, so basically in this case, you'll find greater height, then for example, you'll find the presence of conical peak, steep slopes. These will be your features. Okay. Okay. Before I forget, an announcement for all of you that those of you who would have attended the morning sessions and the morning batches of geography, on Saturday we will be having the session from 7:30 to discuss about the maps, and the doubt clearing session that will be held on Saturday from 7:30 a.m. up till around 11:30 and 12. So whatever doubts that you have had till now, please do send it over to us by mail at IES Live, and we shall be resolving those doubts on Saturday. Other than that, we will be taking up the discussions for mapping. Okay. Now here, that is the case of a mountain. Now here, from the top of the mountains, generally the mountains have such greater height that everything will be frozen, in the sense that water will not exist. Water will exist in solid state, that is in the form of ice. So everything is, that is why, frozen beyond a particular height. Now after that, at that particular height, you will find that as this ice accumulates, this ice tends to move ever so slowly, aided by the influence of gravity. Aided by the influence of gravity, that ice starts moving down the slope ever so slowly. Now, what are these known as? These are known as glaciers. Glaciers are basically your moving mass of ice which comes down the slope consistently with the influence of gravity. These eventual glaciers, when they reach the lower portion closer to the sea level, that is when that ice starts to melt, and that is what feeds the water and gives water for the various river systems that drain the various large areas across the surface. So that is the work done by the glaciers. Now, another feature that you come across quite frequently is that of a hill. So when we talk about a hill, oftentimes you hear about the term hill, right? The Nilgiri Hills, the Satmala Hills, etc. What are these hills? So hills, they are nowhere as high as the mountain. They will generally have a kind of a rounded top, right? Gentle slope feature, which is not going to be very, very steep, a very gentle slope, and a kind of a rounded feature will be in existence. That is the case of a hill. Okay. Now, this is what is referred to as a plateau. A plateau is basically a flat tableland like structure generally created out of volcanic eruptions. So, a flat tableland like structure, tableland like structure. When we talk about how volcanoes erupt, what is the process of eruption of volcanoes, there we will be talking about that how these many of the plateaus also get created. But when we say flat tableland like structure, so flat surface, and steep sides, generally created due to spread of molten lava. That is how the plateau-like structures, they eventually get created. Okay, for example, in the southern part of our country, we have the Peninsular Plateau, the Deccan Plateau. That is basically this kind of a flat tableland-like structure which is in existence. Okay, so you will have steeper sides and flattish top surface. That will be the case of plateau. So we will be talking more about it in the coming days, about how, for example, a mountain, when it is created, at that point of time it is very high, conical, you have glaciers and ice on top, and over a period of time the top portion is eroded, removed away by the winds, rivers, etc., and you have the formation of a hill. For example, in the region of Rajasthan, you have the presence of the Aravalis. All of you would have heard about the Aravali Hills, right? Now, as of now, if you think about Aravalis, the Aravalis, they have not got a significant amount of height. The Aravalis basically, they have got very limited amount of height. And if you take a look, those of you who have visited that place or those of you who have lived in that region, you would always be able to understand and identify it with the fact that you can basically climb up the Aravalis in half a day and come back again. Now, if I tell you that at one point of time in the history of planet Earth, Aravalis were amongst the tallest mountains across the globe. At one point of time, Aravalis had the top peak of it covered with ice and glaciers. You had various glaciers which would originate from the Aravalis and they would continue to come down. But look at it now. So, the mountains, they are created by the internal movement of the planet Earth. The internal forces of the planet Earth, they end up creating and carving out these top mountains, high mountains. But as soon as the internal forces, they weaken, then these get eroded and these get reduced to a kind of a small feature, what you refer to as a kind of a hill. So the Himalayas, as we talk about the region of Himalayas, presently you would hear that Himalayas are the tallest peaks of the world. Fair enough. But that is consistently being uplifted by the interior forces acting across the planet Earth, which we'll study about in detail. We'll study about all these things in detail, don't worry. We'll study about glaciers also, mountains also, hills also, plateau also, everything we'll study in detail. This is just your introductory image so that you have some image in your mind, so that when there is a cross referencing or in the other areas, whenever there is a referencing, you can identify that, okay, glacier is a moving block of ice coming down the slope. Okay, so that is where all the various different features on the land surface, they are acted upon by the forces coming from the interior and coming from the outside surface, such as wind action, river action, etc. Now, that study of the change in landform that we experience around ourselves, that is what is included in the portion of geomorphology. That is what we have to study in the portion of geomorphology. But before we study about these various different forces, the change in the landforms and the change in the land patterns, first of all, let us make ourselves familiar with the aspect of formation of Earth. How is it that Earth came into existence? Bhimare steep side means that the slope is significant. It is like this. So that is steepness. Gentle means like this. Steep is like this. Megha, how Earth is created, sir? Understand, sir, how Earth is created, sir? Okay. Isn't that what we are talking about, Megha? So, okay. I sometimes fail to understand the questions. I'm not getting hill. Hills are, see, if this is a mountain, this will be a hill. Okay, much smaller form, a kind of rounded peak, that is your hill. Glaciers are at the peak of the mountains, at the top portion of the mountains, yes. That mean west of ideal is running 1 day, yes. Shweta, what is cryosphere? The frozen areas, the areas which are frozen, North Pole, South Pole, the region of the Himalayas, the frozen areas. So Megha, I hope that doubt was something else. I am unable to understand what is your doubt here. Can hill turn into a mountain? Yes, it can. Over a period of time, maybe the internal forces will activate its motion, and then again its height will increase. Okay, so basically GMT is the Greenwich Mean Time, that is referred to as the case of the Greenwich Mean Time. Basically is the reference time with respect to what we have the reference of time zones across the world. When we say that what is the Indian Standard Time, how do you measure what is the time standard time of India? Obviously, you will need a reference pointer. You will need a reference pointer. So that reference pointer is your GMT. Now we talk about the case of formation of planet Earth. Now, planet Earth, just like the solar system, came into existence around 4.5 billion years ago. 4.5 billion years back, you had the formation of the star, that is the sun. And basically, it was created as a result of the gases of hydrogen coming together, the molecules of hydrogen coming together, producing significant amount of energy, and thereby in the process producing helium. Right? So you had molecules of hydrogen forming helium. So that would be the case of the process of formation. So here, of formation of the sun. Now, those gases, what you would have studied as nuclear fusion, where two small molecules come together, produce enough heat and energy, and that is where the sun gains its energy by the process of nuclear fusion. But around 4.5 billion years ago, you did not have any planets in the solar system. You just had lot of small particles moving around of various different types of elements, etc. Small dust particles moving around. Now, this entire process of formation of planet Earth is basically driven by certain basic principles. What are those basic principles? Any object which has got mass will have a gravitational pull of attraction. Heavier the object, greater will be the gravitational pull of attraction. Lighter the object, less will be the gravitational pull of attraction. Any object which has got any amount of mass, that will try to pull the other objects by the force of gravity. Okay, it will try to pull the other objects. Now, also another basic principle, whenever you have two objects which will collide, now during the time of collision, heat is produced. Heat as an energy is produced always. Okay, so with that, let us understand the concept of formation. So first of all, around 4.5 billion years ago, you had the sun, which had been formed, and it was significantly unstable at that point of time. Even sun was not very stable, and you had many millions, billions, trillions and trillions of dust particles which would simply be moving around the sun. Obviously, by the gravitational pull of the sun, they would be moving around the region of the sun. Okay. They would be moving around the region of the sun consistently. In a very large area. Now, these were objects of different sizes, but none of them were very large. They were very small. So that is where they would consistently be moving around the region of the sun, and all of them would be in motion, obviously aided by the gravitational pull of attraction of the sun. So when you have multiple particles, millions and trillions of these particles moving around the region of the sun, you would have the situation where there would be multiple such collisions. Hundreds of trillions and trillions and trillions of these collisions would happen every day, because the particles would invariably come into the path of each other. And as I told you, at this point of time, the solar system was not very stable, the sun was not very stable. Okay, so these were the particles which would continue to move around the region of the sun. Now, here, as they would move, there would be collision. And understand that the collision is also of various types. Let's suppose two objects, they simply come and collide like this. Now, it can disintegrate, it can virtually disintegrate into various small pieces. But what if an object is moving like this and another object goes for a collision? An object continues to move, and meanwhile another object coming at a faster speed, it undergoes a collision. In that case, what will happen? It won't disintegrate. It will basically, the collision will produce enough amount of heat, and due to that heat, maybe the objects will get together, isn't it? So the objects would get together after each collision. So you had a kind of a chain reaction. What was that chain reaction? So collisions of particles would happen. These collisions of particles would eventually produce heat. Due to that heat which would be produced, particles could join each other and form a larger mass, right? Because of the heat that is produced, they would basically melt around the region of collision and they would combine and then they would start moving. So when they would join to form particles of a larger mass, larger particles having greater gravitational pull would be formed. Isn't it? Larger particles having a much greater gravitational pull would be formed. And that means these particles would start attracting the other smaller ones. And that would lead to more collisions. Isn't it? More collisions would happen. Again, heat would be produced. Again, more particles would come together. So, like that, slowly and steadily, large sized particles started getting created around the region of the solar system. Very large sized particles, they started getting created. Now, with each of these collisions, as the particle size grew larger, with each of the collisions, the particle would develop a kind of a movement, a kind of a rotation amongst itself, and they would continue to move around the sun. Now, as the size would increase, so rather than having a random motion of the particles, they would now be pulled more strongly by the sun and they would start moving in a fixed path and a fixed pattern. Slowly and steadily, this led to the creation and the formation of very, very large sized objects, which we refer to as planetesimals. So, this process created very large sized particles or very large sized objects. Objects known as planetesimals. These planetesimals would continue to move around the sun. Okay, they would continue to move around the sun. Now, still, you had many of these planetesimals moving around the sun. Now, then came the next stage. So, now, when you talk about the region of the sun, basically, the sun would be surrounded by large planetesimals, which would basically be moving. Large planetesimals, which would be moving around the region of the sun. Now, obviously, these would consist of various different materials and elements which would be created right at the time of its formation, and the properties of these dust particles eventually, depending upon what kind of materials were present. Many of the new elements were also created, but you had various different particles which would be consistently moving. These would be your planetesimals. Now, these planetesimals, which would be at various different distances from the sun, they had significant amount of mass, significant amount of gravitational pull. And that is when they would collide. One or the other would come in the path of each other, because the solar system, again, remember, was in its very formative stages 4.5 billion years ago. Solar system was in its very formative stages. Solar system had not evolved. So that is why it was unstable. And many of these planetesimals would be floating around. It was nowhere close to the solar system that you see today. Now, These planetesimals, they underwent multiple different collisions, and each of these collisions would produce a lot of heat. And with each of the collision, these planetesimals would get a kind of a spin associated with them. They would have a certain axis which would be created with each collisions, right? Eventually, the heat due to these collisions would be so significant, it would melt the objects. Multiple of these planetesimals, they would come together, and that led to the formation of the primitive Earth. Primitive Earth was formed. This is your primitive Earth. Earth. Now, this primitive Earth that we talk about, this was formed as a result of these multiple collisions of these planetesimals. So the heat produced was very high. As the heat produced was very high, what would that mean? That basically would mean that the materials would get into a kind of a molten state. The materials would start melting. So here it was nothing but a hot molten spherical object. Everything was in a liquid state, molten state, because the temperature was very high. This I'm talking about around 4.5 billion years ago. Now, everything was in a molten state, and you had various different types of elements present. Now, whenever you talk about liquid and different types of liquid, if you mix together, all of them, it is not always going to present a kind of a homogeneous mixture. For example, if in a glass jar you pour water, you pour honey, and you pour oil. Let's suppose you pour honey also, you pour water also, and you pour oil also. Now, will all of them form a good solution? Will all of them be able to mix uniformly? Absolutely not. Honey, being the heaviest one, will settle at the bottom, then will come water, a layer of water, then will come a layer of oil. So, at this stage, the heaviest elements which were present at this stage, they started settling at the bottom. The heaviest elements which were present at this stage, they started settling at the bottom. So here, the heaviest elements, and at this point of time, heaviest elements which were present were iron and nickel elements started settling. To the bottom. Okay, they started settling to the bottom. So, for example, if let's suppose you had, now by the way, again another thing that students sadly they get confused in this. When I say bottom of the planet Earth, what do I mean? Do I mean this point A, or do I mean this point B? What is the bottom of Earth? Okay. This is what I was afraid of. Okay. So when you think about the region of Antarctica, guys, what is the imagination that you have? People are standing upside down in the region of Antarctica. If you go to Antarctica, do you think people have to stand upside down? Is that the kind of an imagination that you have? That it is the bottom of the planet Earth, so someone who is standing here will simply fall off into the outer space? Is that the case? All of those who said that bottom is at B, I won't be naming you guys, But think about it for a brief moment. How do you think that bottom would be at this region? Bottom is always around the region of the center, the core. Okay, from all sides, if you go to the bottom, from all different sides, if you go to the bottom, you will reach the region of the core. You will reach the center. So bottom is always the center. That is core of the earth. And at that point of time, the heaviest elements were iron and nickel. That is what started settling to the region of bottom. And that formed the core. Even today, when you talk about the core of planet Earth, even today, the core is consisted of mainly iron and nickel is what dominates the core of planet Earth even up till today. Right? So that is how basically you had the earliest formative portion of planet Earth. But still, the solar system was not stable at this point of time. You still had millions and thousands and millions of collisions happening with this molten portion, where you had small objects continuously crashing into this molten portion, getting melted down as well, and adding to the portion of planet Earth. At this point of time, you had another massive collision which happened, and collision with respect to planet Earth, another massive collision which happened. So, here, when you talk about the collision, you had a Mars sized object, a large Mars sized object, which was coming in the path of planet Earth. A large Mars sized object. Sized object coming and colliding with molten Earth. This large Mars sized object, this was named as Theia. Mars sized object, what are the interpretations of Mars sized object? What is the English meaning of Mars sized object? Think about it. What can be the meaning of it? Means an object which has a size, which had a size which was similar to the size of Mars. That is what is the meaning of Mars sized object. Is that difficult to understand? Okay, I hope that is not difficult to understand. Basically, that Mars sized object came and collided with planet Earth. Now, that collision was huge. Earth was in a molten state, and this object went and simply crashed onto the planet. So, this object also got disintegrated. Some portion of it was thrown away. And along with that, many of the molten portions of the planet, they were also thrown away. Along with the objects of Theia, many of these molten objects, they were also thrown away. But then, planet Earth by that point of time had become so large that its gravitational pull of attraction was very significant. And it basically could take away the top surface, the top portions of planet Earth. It was molten, obviously. So the top portion basically was carried. Imagine a large ball which is molten and another object which comes with a force and crashes with that. So some of that other object, foreign object, will also get dismembered. Some of that foreign object will also go away. Along with that, lot of molten particles on the surface will be splashed away. It will create a huge splash. Lot of these materials will be thrown away. But by that point of time, the planet Earth had got a very distinct gravitational pull of attraction. So, that gravitational pull of attraction meant that planet Earth did not let these molten particles fly very far away. And these molten particles, they were held by Earth's gravitational pull. Slowly and steadily, it was continuously held because of the Earth's gravitational pull. And it would continue to move around the planet Earth owing to the momentum of that crash. That object, which is held or which was held by planet Earth due to its gravitation, is still held by planet Earth due to its gravitation, and still today that object continues to move around the Earth's surface. And that is what we refer to as the moon. That is how moon was created. So moon was created as a result of a very giant and a big impact. And that is why formation of moon is what is also referred to as or provided by giant impact hypothesis. It was that giant impact with Theia which led to the formation of moon. How do we know that? How do we know what happened 4.5 billion years ago? It was only in the last century or in the last few decades when the Apollo missions, when they went to the moon, they brought certain rock samples. And analyzing those rock samples, one got an idea about how these would have been created. They have the same origin, same time scale of origin as compared to the planet Earth. And basically, few of the rock particles, they have the evidence of some foreign object as well. So that is basically also tells us analysis of the particles of the moon. That tells us that it is only the lighter portions and the lighter particles of planet Earth which were carried away and led to the formation of the moon. And that is after the Apollo missions of the 70s and the 80s. That is when we came to the conclusion that this is how the moon could be formed. Recent findings have indicated something very unique. By various seismic waves and instruments by which we study the interior of the Earth, it has been found that underneath the region of Africa, you have the evidence of this Theia. Underneath the region of Pacific, you have still a very hard solid mass, very deep obviously in the interior, which tells you that as this Theia would have come and crashed onto the planet, some portion of it would have flung away, but it would have disintegrated, it would have broken into two larger pieces, and because the planet Earth was molten, it started settling down and sinking in the interior. It is still to be found underneath the region of Africa and underneath the region of the Pacific. Now, don't get here childish ideas that does that mean that if we dig a hole in Africa, we will get to look at Theia? We are talking about great depths of many 100 kilometers deep, where you will have the evidence of this. Okay, so that is how the planet Earth came into existence, and that is how the moon was created. But after this, still the planet Earth was in a molten state. And by this point of time, the heaviest elements had settled to the center, that is the core. But what about the other state of planet Earth? We do know that planet Earth is no longer in a molten state. We do know that we refer to planet Earth as a kind of a blue planet. How is it that Earth basically became a blue planet? So, then came the process of evolution of planet Earth. This is the basic formation. Then came the evolution of planet Earth. So let us talk about the evolution of planet Earth. So observe here Basically, in the time of formation, you had multiple of these planetesimals which crashed together, produced enough heat, they got together, formed a larger particle which would then move, crash with the other ones, and that was the process of formation. But when we talk about evolution of Earth, how did that happen? So, planet Earth was in a molten state. Heaviest elements had settled at the bottom. Slowly and steadily, the number of collisions across the solar system reduced drastically because most of the smaller particles were already undergoing collisions somewhere or the else. So slowly and steadily, number of collisions they came down. They basically were reduced. And eventually, you had this as the planet Earth, which started becoming stabilized. And when the number of collisions reduced across the solar system, planet Earth also experienced some amount of cooling. Now, it was a hot molten liquid ball of mass. So think about it. Cooling would happen from the outside or cooling would happen from the inside? What do you think? Would the cooling happen from outside or would the cooling happen from inside? Very good. Cooling would always happen from outside because it is from the outside that it is in contact with the colder areas outside. Inside it is very hot. So cooling started happening from the outside. For example, when you boil milk, right, when you shut off the stove, after some time, if you touch the surface, it is slightly cooler. But if you dip your finger into the milk, the interior portion of it is very, very hot. Isn't it? The interior portion of it is significantly boiling hot. So that means the interior is very hot, the surface is cooler. So cooling always happens from the surface. Here also, the cooling started to happen from the surface. And that is when, as it cools, it starts developing some wrinkles, few areas they remain in an uplifted portion, few of the areas they get depressed, because that is how it cools. Even when you let's say we talk about the cooled portion of milk, when the milk cools down, you will observe that the top surface of it develops a thin solid layer, which is not going to be always plain. It will have some wrinkles developed into it. So that is when slight wrinkles developed. Few of the portions they had depressions, few of the portions they had some amount of upliftment. But in the interior, the temperature was still very high. So here, cooling started to happen. Cooling was initiated. From outside. And the interior remained very hot. Even today, we have the same scenario. The interior of Earth is still very hot. And over the next 3 to 4 classes, we will see that all these events, earthquakes, volcanoes, formation of mountains, creation of oceanic trenches, everything is basically driven by the interior heat of planet Earth. That heat still remains in the interior. Now that heat which remains in the interior, which still drives the major forces of the planet, for example, formation of plateaus. I hope you are aware. If you are not aware, most of you would not be aware, in fact. Every few areas and after every few million years, due to the internal heat of planet Earth, you know what happens? The land simply gets pushed up in certain areas. The land simply gets uplifted. And that is, if you have to think about it like, for example, you have some solid substance, any solid substance. iron, any of that, plastic. If you provide heat from inside, it swells up. It kinds of gets inflated, isn't it? Something similar happens on the Earth's surface also. Because the heat in the interior is so high, every few years, rather, when we say few years in geography, it is not like history or other subjects. Here, every few years, we are talking about every few millions of years, hundreds of millions of years. The land simply gets uplifted. Sometimes, due to the heat, the land simply comes down. So, that heat is still a dominant factor across the various parts of the planet. This is what is also known as the residual heat, or the heat which remained. So, this is known as residual heat. That is what we consider and what we know as the residual heat. Now, in this case, the cooling had been initiated from outside, and in the interior everything was still molten. Slowly and steadily from outside, things started cooling down. By cooling down, if a liquid cools down, it becomes a solid. So slowly and steadily from the outside, things started getting into a solidified state. Rocks started getting created. Earliest rocks got created, and we have evidence of that. Rocks dating back around 3.5 billion years ago. We have the evidence of that. Certain areas in Australia, the rocks have an age of around 3.5 billion years old. Forget Australia. In India, when we talk about the region of Jharkhand, the Chota Nagpur Plateau, you have the evidence which indicates that might very well have been amongst the first few land masses the planet had witnessed. But we'll come to that. We'll come to the formation, creation of land masses. Now, still in the interior, many materials, different types of materials were in a molten state. And along with that, you had gases. Molten materials and gases were trapped inside. Okay? Molten materials and gases were trapped inside. Now, here you might have a doubt. How come gases? It is okay as long as you were telling me that molten material, I could still wrap my hand around it. But how come gases? So think about it. When we talk about any kind of material, let's suppose alumina. Alumina is what? Or silica. Silica is SiO2. Iron oxide, Fe2O3. Hydroxides, OH. Right. Now, if you basically melt this, SiO2, silica is in a solid state. The sand particles that you have, that consists of silica, it is in a solid state. But it has got oxides. If you melt it, what will happen to the oxygen? Oxygen will get converted into gas. Right? Oxygen will get converted into gas. So like that, you had various different gases which were trapped inside, and the outside had started solidifying. But it was still solidifying. The outside surface was nowhere as strong as what we have today. It was still solidifying. It was in the process of solidification. So that is when the earth went through a phase, what is known as the phase of degasification, where from various different areas, these gases are always lighter, isn't it? Gases are basically lighter. So being lighter, they will try to rise to the surface, and they will bring the molten materials along with them. So the gases, they started exiting the interior of the planet, and the surface was not very hard. Again, recall the moment when you have basically just had some amount of cool milk. So, on that case, you have the surface, which develops a very thin solid layer. But if you poke your finger into it, that solid can easily be broken. Right. So, that was the condition of the Earth's surface. It was solid, but not very hard. The planet entered into the phase of degasification. Phase of degasification. Now, when we say a phase of degasification, what do we mean by that? We basically mean that the gases trapped in the interior, they started erupting out. They started moving out of the interior. They broke through the surface, bringing molten materials again to the surface. So you had millions and billions of volcanic eruptions which would happen. A lot of volcanic eruptions would happen on a daily basis in different parts of the planet. So, gases trapped in the interior, trapped in the interior, started to escape, which brought the molten materials along in the form of multiple volcanic eruptions. Multiple such volcanic eruptions happening on a daily basis. Now, amongst these gases, few of the important gases also escaped. And when I say few of the important gases, you had gases such as ammonia. Ammonia was one of those gases. Methane was one of those gases. So you had NH3, CO2, CH4, O2, oxygen as a gas was released. Along with that, you had sulfur, sulfates, significant amount of hydrogen. Now, hydrogen and oxygen at that high temperature would fuse together. And that is what led to the formation of water vapor. Vapor, H2O, would also be released. Now, these gases started circulating in the atmosphere. And this period, by the way, this continued for many millions of years. We see a volcanic eruption nowadays. We think about it, oh my God, what is happening to the planet? Are the gods angry with us? That volcanic eruption has been continuing for a month. Think about a period and try to imagine a period in planet's history where these eruptions would continue not only for a few months, not only for a few years, not only for a few centuries, not only for a few millennium, for hundreds and thousands of years, multiple times of that, for many millions of years, you had this consistent amount of gases getting released because Earth is a massive object. So, that phase of degasification expelled these gases from the interior. Then, for a brief period, there was a kind of a lull. Lull as in, you did not have many of the volcanic eruptions at that point of time. So again, that process of cooling down accelerated. So then, as the process of cooling down continued. So that is when phase of cooling. Again, this phase of cooling down accelerated, where if you consider the planet Earth, now the outer surface started solidifying further significantly. It was already a solid with various different types of deeper areas, uprised areas, etc. But that was it. Barren rocks were present. That's it. And over the period of many millions of years, as these gases they would surround, the phase of cooling happened. Now it was in this phase of cooling when water vapor combined with gases, ammonia, dust particles, etc., and they started forming dense clouds. Very significantly dense clouds were created. Very, very thick, dense clouds were created. And these clouds would virtually wrap the entire planet within itself. Now, think about it. A planet which is cooling down now has got that cloud cover. So, sunlight is blocked almost perpetually. That is when these clouds cool down even further. And then came the phase of torrential rainfall. Phase of torrential. Torrential means torrential means what? Torrential means something which is very heavy, which is very continuous. That phase of torrential rains, that start again, how these clouds were created? These clouds were created as these gases they started emerging. These gases they started emerging. You had water vapor, etc. As this cooling accelerated, these gases they formed clouds. So let me write down here itself. So gases cool down to form very dense clouds. Now, further that cooling was accelerated because it would hide the planet from sun. Continued darkness, it became cooler and cooler. And then it rained. It rained and it rained and it rained. In whichever area that you are living in, if it rains for one day, everything becomes very damp and wet. If it rains for 4 to 5 days, whichever region you are living in starts getting flooded. Imagine a rainfall which continued for continuously around thousands of years. Few estimates tell us that it rained for around 2 million years continuously. But many of the geographers don't agree with that. But the conservative estimate is that it rained continuously for close to around 10,000 years. All the ammonia, then you had sulfates, carbonates, everything, methane, everything combined with water, and it continued to rain. So, this was a phase of torrential rainfall where it continued to rain for 7,000 to 10,000 years. That means what? All the low-lying areas that got filled with water, and it continued to get filled with water. You had the formation of the oceans and the seas of the planet. And that further accelerated the rate of cooling. The surface started getting harder and harder. And eventually, the interior, from the surface that cooling happened, and the outer surface cooled, the middle surface cooled, but the interior was where the heat remained trapped. Because as the outer surface cooled, there was not many areas from which the interior molten heat could escape. So the heat got trapped in the interior. The heat remains trapped till today in the interior. That is the residual heat. So this basically accelerated, this not only filled up the seas and oceans, and accelerated the rate of cooling. In the interior, you still had the portion which was molten, and in the interior, you still had basically the presence of that heat, which is referred to as residual heat, which continues to remain trapped even today. So, almost around 3.8 to 4 billion years ago, that is around half a billion years since its formation. Half a billion years is not a short span of time. This entire thing happened around 700 million years to 800 million years, we are talking about. In that 700 to 800 million years, these things happened. And that is when the planet started to settle down. And around 3.5 billion years ago, you had the germination of life. Life started because the ground surface was still a harsh condition, very harsh. Ground surface would still experience volcanic eruptions here and there. There was nothing but hard rocks. But oceans, they represented a kind of a calm condition. Oceans represented a region of calmness. That is where small celled chemotrophs, that is, those microbes which can utilize the chemicals around them to produce food, these chemotrophs, they started coming into existence. And that was the genesis of life. That is how life originated. And for the next couple of billions of years, life existed only underwater. It is only when you would study in the portion of environment, it is only when the conditions started becoming harsher in the oceans, life migrated to the land. But for a long period of time, life remained only underwater. Slowly and steadily, when these microbes, they found out that okay, carbon dioxide is present in a dissolved state in the water, they could basically use that carbon dioxide, oxidize it, get enough food, manufacture carbohydrates. They could sustain themselves. When they could sustain themselves, they would multiply. Like that, multicellular organisms came into existence. You had some of the, and generally most of these organisms would be situated in the shallower areas of the oceans. That is where the water would not be very deep. Still, the deeper parts of the ocean is said to have been denied of any form of life because the conditions at the bottom were also very harsh. That is how the planet Earth came into existence. And this entire journey, which has happened over the span of 4.5 billion years, that is very unique. Where you will find that the planet has not been disturbed by a major massive collision. ever since that time of uncertainty around 4.5 to 4 billion years ago. Planet has not been disturbed by a major massive collision until around 65 million years ago, when you had another such massive asteroid, which basically came into the path and collided with planet Earth. And that created havoc. That put to an end to the most dominant species that planet Earth had ever witnessed, in the form of dinosaurs. Otherwise, if that collision would not have happened, maybe you and I, we would never have been in existence. We would still be living in the era of dinosaurs. And one of the latest research papers, which have been published only this month, it basically tells us that the only reason that we mammals, we do not have a long lifespan. We have a very short lifespan. We end up maturing, and basically the reproduction happens, and we end up dying by the age of 60 or 70 years, is because of the dominance of dinosaurs. It was because of the dominance of dinosaurs that the mammals, they learned that if you have to survive, reproduce fast, because you never know when you might die, you might be consumed. That asteroid, which collided with the planet Earth 65 million years ago, that took care of it. And now we mammals, we dominate the planet Earth. So that is about the entire evolution and formation of planet Earth. Now, the formation and evolution of atmosphere we will study in the portion of climatology. Now, direct question is never asked in general studies that talk about the formation of planet Earth. That direct question will not be asked in GS. Here, you can have a pinpointed statement being asked from it. For example, you can have a question that oxygen was always present in the atmosphere of planet Earth right since its formation. Will that be a correct statement, or will that be a false statement? What do you think? Oxygen has always been present in the planet's atmosphere right since the time of formation of planet Earth. False? Right? So, this was a question which was asked in 2018 prelims examination. So, if you understand this process of formation, as we move ahead into the interior, even that would be understood very easily. Okay, so a quick recap. Basically, what started? It started with the formation of the sun. How did the sun come into existence? You had the gases of the lightest elements of hydrogen came together. Nuclear fusion happened. Hydrogen collided to form helium. Right? Nuclear fusion reactors you would have studied. So that produced heat, energy. Sun started getting created. Large mass. It had its own gravitational pull. Various dust particles were floating around. As these dust particles were orbiting across the sun, then they went through multiple of such collisions. With each collision, there would be heat which would be produced. So the size of the particles would continue to grow larger and larger and larger. As these particles would continue to grow larger, they would have their own gravitational influence. They would have their own gravitational force of attraction. And that gravitational force of attraction, or that gravitational pull, would lead to more collisions. Eventually, they led to the formation of those early objects, which are referred to as the building blocks of these planets. That is what we refer to as planetesimals. These planetesimals, they came together and they collided to form the planet Earth. And like that, many different planets. And that is when, as the planet Earth got created, at that point of time, the heat was so high that it was in a hot molten state. Heaviest elements of that point of time, that is iron and nickel, they started settling down. They settled down at the region of the bottom of the Earth, that is the core of the Earth. And it still forms the dominant portion of the core of planet Earth. Then after that, as these number of collisions, they reduced, planets started becoming stable. But as it was happening, a very large object, almost to the size of the Mars, that came and collided with the Earth. That object was named as Theia. Now, due to that giant impact, portions of the top surface of Earth were basically removed off, and it continues to orbit around the Earth even today, and that is the Moon. That is why the formation of Moon is referred to by, or can be understood by, the giant impact hypothesis. After that, again, as the planet became stable, it started to cool down from outside. The surface started to cool down, but you had so much amount of molten materials and gases which were trapped in the interior that the gases wanted to exit. The gases, they tried to escape. As these gases would try to escape, they would basically puncture the surface and emerge outside. And you had the phase of degasification dotted with hundreds of millions of volcanoes and volcanic eruptions continuing for many millions of years. It was at that point of time when you had gases such as methane, carbon dioxide, oxygen, hydrogen, some amount of oxygen, not in the quantity that you find today, for a long period or up till very recently, that is up till around 300, 400 million years ago, 400 million years ago, oxygen was amongst the little amount or the minor gas which you would find in the atmosphere. Now, at high temperatures which were prevalent, oxygen and hydrogen combined to form water vapor. You had so many dust particles emanated outside because of these volcanic eruptions. Oxygen, hydrogen, etc., they combined to form the earliest clouds. Those clouds would consist of various gases, ammonia, methane, etc. And after that, when that phase of volcanic eruption stopped, again that process of cooling was reinitiated. During that cooling, cloud formation became prominent. You had a very thick cloud cover which covered the entirety of the planet Earth. And then it rained. It rained, it rained, and it rained for thousands of years. And that is what filled up the earliest of the seas and the oceans. And that is when the planet was basically converted into a blue planet. And basically, after that phase of torrential rainfall, that cooling accelerated, reducing the heat trapped in the interior to the region around the core and the region somewhere around the mantle, but rest of it, the entirety of mantle and the top portion were solidified, and in the interior, it is still in the molten state. That is the residual heat. So that is the entire process of formation of planet Earth. Okay? I hope that is understood. Right? Now, after this, we move ahead to the portion of the interior of Earth. So basically, when we talk about the interior of Earth, now about the question that where did iron come from, where did these elements come from, so all these dust particles which were there, they had the presence of few of these elements, many of these elements. That is why you send the space probes. You recently had the space probe which went to the asteroid and collected some particles from asteroid and returned to the planet Earth. Right? It is from this analysis, the earliest particles that we get an idea about what would be the condition of the particles which would have collided. So these elements were brought by the collisions. Okay. Now, after this, you have the case of interior of the Earth and the interior structure of planet Earth. So when we talk about the interior of Earth, what is present in the interior? Or what is the structure of planet Earth? So the structure of planet is still collision taking place. Have you heard about a collision taking place around you, my dear friend? Have you experienced a collision in your area now? You still have objects which come, few of the collisions which still happen, but now the sun has, the solar system has settled down. Now you don't have many objects moving around. It is only between Mars and Jupiter where still you have a lot of particles moving around, that is the asteroid belt. But other than that, the solar system has largely settled down. So obviously, no particular collisions. Now, after we move ahead to the portion of interior. When we talk about the interior of planet Earth, here it is always likened to that of a structure of a coconut. Now, all of you would have seen coconut, the ripened coconut, basically where the outer structure, the outer part of it, that is hard, but it can break easily. Then you have the inner whitish shell, isn't it? That whitish shell or the inner whitish layer, the pulp of the coconut, that is solid. But it is that kind of a solid, if you press it, it can be compressed. If you stretch it slightly, it can be stretched, isn't it? That is the region of the mantle. And then the coconut in the inside consists of liquid. Like that, planet Earth in the inside also consists of molten materials. So that is why the interior structure of planet Earth is always likened to that of a coconut. But how do we get to know what is present in the interior? Has someone gone to the deeper portion and to the core of the Earth to find out what is present in the interior? Obviously not. As you start digging into the planet Earth, the temperature starts rising up so significantly, you cannot dig beyond a point. But we have other sources of information. So, many of this idea about what is present in the interior of planet Earth, that started getting clearer in the early 1900s, in the first couple of decades of the 1900s. So here, basically, when we talk about it, the interior of Earth, you have the sources of information. Sources of information for the interior. Now, these sources of information about the interior, they can basically be brought into two parts: direct sources and indirect sources. Okay, when we say direct sources, we are basically talking about where you get the direct evidence of what is present in the interior. For example, volcanic eruptions. Volcanic eruptions. So volcanic eruptions basically means molten materials from inside, they come up. By analysis of that molten materials, we get an idea what kind be the chemical composition of the materials present in the interior. So that is where the volcanic eruptions, they give us an idea about what is present in the interior. That is why every time when a volcano erupts, you will find various different geologists, scientists, they go with all the protective gear, they go to the site of the volcanic eruption, they start collecting the molten materials, keep it in a bucket, and they analyze it for years altogether. And by that analysis of that solidified material, the particle structure, the chemical composition, the property, they get an idea that this molecule would have experienced what kind of pressure from above. Which portion of the interior is this coming from? So what is the interior of the planet? So that volcanic eruption is one of the direct sources. Then other direct sources, or the other direct source, is basically mining and digging. But the deepest mines across the planet, they don't go deep enough. When we talk about the radius of planet Earth, are we aware about what is the radius of that spherical Earth? Earth has got a radius of close to around 6,370 kilometers. 6,370 kilometers. That is the radius which carries you to the interior. So if you start digging, imagine how much time will it take for you. And obviously you are digging into such hard rocks, you won't be able to drill beyond a particular region. The deepest mines, which exist in the region of the Kola Peninsula in the northern portion of Eurasia. The deepest mines have a depth of around 10 to 12 kilometers itself. But that in itself gives you enough idea that as you start going deeper, the temperature increases. As you start going deeper, the materials, they start getting compressed. Different type of materials will be found there. So that is the case of mining and digging. That idea is given to you. Then indirect sources. These are your direct sources, direct set of information. But analysis of many different ideas and many different pieces, they give you an idea about the interior. So what are those indirect sources? So first is seismic waves. Whenever an earthquake occurs, it releases so much amount of energy that the energy travels in the form of waves. We will study later what is known as the seismic waves. Now these seismic waves, they travel through the portions of the interior of the planet, throughout the portion of interior of the planet. Analysis of the seismic waves give us an idea that from which region have they traveled, that region is in a solid form or a liquid form. We will study more about it when we talk about earthquakes. So indirect sources, seismic waves. Then after that, study of the meteors, the asteroids, because they give you an idea about what the particles moving around the sun 4.5 billion years ago, what they would have looked like. Okay, so it is those collisions which had led to the formation of planet Earth. So an analysis gives you an idea about what that would look like. So there, basically, asteroids and meteors. Then the planet Earth extends a kind of a magnetic property. It behaves like a magnet. So studying the magnetic field gives you an idea that what is present in the interior which extends that magnetic field. We have studied yesterday that the planet Earth is in a shape of a geoid where it is slightly bulged around the region of equator. It is slightly flatter around the region of the poles. So that basically studying the gravitational and the magnetic fields, that gives you an idea about the interior structure and the materials composed in the interior. So here, magnetic and gravitational anomaly. Forces and anomalies. Okay. So with these sources of information, we get some idea about what is present in the interior. Okay. We'll move ahead further with this. Before that, we take a break. So let's take a break and let's be back and we will continue with this discussion. We'll talk about the structure of the interior as we move ahead. So we take a break of 15 minutes. If a small particle is attracted by a large particle due to pull force, why Earth is not pulled by sun? How does the Earth revolve around the sun? What do you think? Is there a heavenly body out there from whose blessings the planet rotates around the sun? What do you think is the force which makes the planet move around the sun? Web of asteroids basically is the asteroids, the study of the asteroids. The asteroids, they still indicate what the earlier solar system would have been.